Hello, my name is Hunter Gonzales, and for my General Chemistry 1 Capstone final project, I'm going to try and answer the question, how do we close the hole in the ozone layer? If you've ever taken any kind of science course before, you've probably heard of the term ozone layer before. If you were like me when you first learned the term, though, then you probably don't really know much beyond it, that it just protects us and that it's being damaged by climate change. But today I want to take a closer look at exactly what the ozone layer is, where it came from, and look at other aspects such as how it protects us, the actual extent of ozone depletion, and what we can do as humans to repair the damage that's been done to it. To begin, let's talk about exactly what the ozone layer is and even, where it just came from. The process started over 2 billion years ago when early aquatic life forms called blue-green algae, also called cyanobacteria, began to use sunlight energy to convert water molecules and carbon dioxide into organic compounds, commonly known as glucose, and letting off oxygen as a byproduct. This process is popularly known as photosynthesis, as much you probably know, but as this process continued, some of that oxygen that was released started to accumulate high in the atmosphere about 15 to 30 kilometers up, or about 9 to 18 miles up, and above the Earth's surface is that area known as the stratosphere. That's where it all started to accumulate, and that molecular oxygen, that O2 that accumulated in the stratosphere, was exposed to high amounts of solar ultraviolet radiation, also called UV light, UV radiation from the sun. And this interaction between the molecular oxygen and the light started to split it into its two individual oxygen atoms. As a result, this atomic oxygen was now able to react with the molecular oxygen in the atmosphere and form O3, also known as ozone. This reaction now allowed ozone to constantly be building up in the stratosphere, and eventually the ozone layer as we know it started to form. So now that we know where the ozone layer came from, let's talk about what exactly the ozone layer does for us and why it's so dang important. As previously stated, the ozone molecules in the atmosphere absorb ultraviolet radiation, specifically UVB and UVC light emitted from the sun, and this process is very important because this kind of UV light can cause a plethora of different kinds of problems for all life on Earth. When exposed to high amounts of this kind of radiation, it can cause, so many different problems ranging from a simple sunburn all the way to deadly skin cancers. It's also been known to cause problems involving eye damage, immature skin aging, and weakness of the immune system. And these problems aren't just limited to just humans. Animals and plants are also negatively affected by UV light exposure, very similarly to humans. Before the formation of the ozone layer, life was not even possible on Earth. But thanks to the ozone layer, we could freely go outside and have that protection from the UV light. Without it, all life on Earth would actually just die. Now, with all that being said about how the ozone layer actually protects us, there has been many problems that have become very relevant in recent years regarding the ozone layer. Now, normally the ozone in the atmosphere undergoes a constant natural cycle of being broken down and then rebuilding itself. And this allows the ozone layer to renew itself and continue to absorb that harmful UV light. But after the Industrial Revolution, due to the use of ozone depleting chemicals and the increase of climate change, the natural cycle of the ozone layer has been disrupted. Chlorofluorocarbons, also called CFCs, have been in the spotlight as the main perpetrator for ozone depletion for the past few decades. CFCs were commonly used chemicals for pretty much a bunch of everyday items like aerosol sprays, packaging materials, and refrigerants. Although CFCs are not directly harmful to humans, it's mostly benign in small amounts, they have been known to be the leading cause of ozone depletion, which has caused a plethora of problems as previously stated. The accumulation of CFCs in the atmosphere was allowed to persist for a very long time, and holes in the atmosphere in the ozone layer started to begin to form. Studies conducted and also satellite imaging of Antarctica have shown a large amount of areas with low ozone and also high amounts of UV radiation. In this area above Antarctica, it has been labeled as a hole, and at times it's been the size of Russia and even the size of North America at certain points. If the hole in the ozone layer were allowed to persist, it would keep growing larger and larger, and dangerous amounts of UV radiation would eventually reach the Earth's surface. Now, with the rapid depletion of the ozone layer and the impending problems that can come with it, it's natural that we as humans would want to do something to try and fix this problem. Lucky for us, a majority of the work has actually already been done in order to replenish the atmospheric ozone. Back in the 1980s, this was a huge problem that needed to be solved. The hole in the ozone layer became very famous around the world, and people started to unite to try and find a solution. Now, what was the actual solution to the problem? It was to stop the production of CFCs. the leading cause of ozone depletion. Campaigns around the world began to start to go and ban CFCs, and by September 16, 1987, the Montreal Protocol was signed by 197 different countries around the world and officially had the ban of CFCs. This is considered the first universal treaty and actually the most successful global action for environmental protection. Because of the Montreal Protocol, the hole in the ozone layer has been able to slowly repair itself, and over the years there has been other ozone-depleting substances such as hydrochlorofluorocarbons and methylbromine, and these have been banned as well due to amendments added to the Montreal Protocol. Today, nearly about 99% of all ozone-depleting substances have been made illegal through the Montreal Protocol and its amendments. With all the work that has been done to repair the ozone layer, scientists actually hypothesize that the hole in the ozone layer will be completely filled in by the year 2060. Despite all the efforts that have been made, there's still some growing concerns that could lead to further complications in ozone depletion. Even with the Montreal Protocol, CFCs and other ozone-depleting substances have not been entirely wiped out. Certain medical items, such as inhalers to treat asthma patients, have been exempt from the Montreal Protocol, and some countries have even been known to illegally produce CFCs. Beyond the continued use of CFCs, there's also large amounts of them still lingering inside the atmosphere and even the oceans. The CFC contained within the oceans has also become a recent topic of concern. Due to other environmental issues such as climate change and increased global temperatures, the oceans cannot properly store CFCs anymore, and they may even begin to emit those back into the environment and continue ozone depletion. Scientists have predicted that by the year 2075, without climate change, oceans will be emitting more CFCs than they will be able to absorb it. And with climate change, that may even happen as close as 10 years sooner. The solution to this problem is not as easy as, banning a few substances like they had to do before with the Montreal Protocol. This would cause for a global effort to stop climate change. Efforts to stop climate change have already been in effect for a long time. Everything from switching away from fossil fuels to renewable energy, using public transportation instead of cars, recycling, limiting food waste. These have all been done to try and combat climate change. But the solution will not just happen overnight. But the significant efforts to heal our ozone layer has given us a great start. And if we continue with these efforts, the hole in our ozone layer and many other environmental problems may just be a thing of the past. Now that we've had the opportunity to discuss the ozone layer in detail, let's discuss some of the chemistry that's actually involved with the ozone layer and how it relates to some of the topics that we've learned in General Chemistry 1. To start off with, let's discuss the chemistry and the reactions that are involved in the ozone-oxygen cycle. To begin, molecular oxygen, or O2, is normally in its diatomic state, but when it absorbs ultraviolet radiation between the nanometers of 100 and 400, it is broken down into its two individual oxygen atoms. These free atomic oxygens are now fast-moving atoms, and they collide with other gases in the atmosphere, such as other molecular oxygen and even nitrogen inside the atmosphere. When it gives out its energy to these other gases, it releases thermal energy that heats up the stratosphere. The oxygen atom then slows down and is able to make a weak covalent bond with other molecular oxygen, forming O3, or ozone. This ozone then absorbs more UV light, and it breaks off into single molecular oxygen again, and it becomes another fast-moving atom. Ozone is then remade, and when oxygen atoms slow down again, the cycle begins to continue again. Here you can see a Lewis structure of ozone. You can see that it has a double bond here where it had a molecular oxygen, and this atomic oxygen is weakly bonded to that molecule there, making O3. You can also see here the molecular formula. When it starts off, it's 1O2, and it gets broken down by that sunlight into two individual oxygen atoms, and then that individual oxygen atom and the molecular oxygen O2 forms together to make ozone. Then once it's broken down again, that ozone is hit with another UV light and is broken down into molecular oxygen and atomic oxygen.